Now, when we talk about logarithmic and exponential equations, we have to do a few ideas. We'll talk about this aspect on our backside, and you can move that down in our notes. But generally, when we talk about exponential equations, we were dealing with questions that were like this. 2 to the power of x equals 2 to the power of 5. Well, as long as our bases are the same, then x equals 5. All right. So what we're going to do is we're going to solve some of these logarithmic equations. Now the good news is we're going to solve the same way that we've been doing it for the past 2 sections already. We're just going to apply that whiplash method. We start with our base, 6 to the power of 11 equals 2x minus 1. So this whiplash allows us to get rid of that logarithm when we have a base, and it allows us to, well, as long as we only have that one logarithm. We'll talk about other cases, but when we type this in, a 6 to the power of 11 is 362,797,056, and that would equal 2x minus 1. Now to finish off our equation, we would add the 1 to both sides. So we'd have 362,797,057 would equal a 2x, and then divide by 2 to get our x by itself. So we'd have, as an exact number, yes, this one would work out nicely as a decimal, but 362,797,057 over 2. I'm not going to worry about checking this answer because we'll have 2 other questions that we'll actually be able to check. But trust me that if we were to plug this in, it would work out. All right. Now, we're not going to check this one either. We're going to actually check question C before we come back to B. Now, in this question, we have a logarithm on both sides, but we also see that we have this 1 on this side. Now, because of that 1 on that side, overall what we want to do is we want to get our logarithms to both be on the same side. So in order to get rid of an add log x plus 1, we would have to subtract a log of x plus 1. So that we would get log of 8x plus 4 subtracting the log of x plus 1 would equal 1. Now if we go back to our logarithmic laws from our last section, when we have that subtraction, it means that we're going to divide these 2 arguments. So we actually have the log of an 8x plus 4 over an x plus 1. And that would equal 1. Now that we only have one logarithm, we can apply that whiplash. The standard logarithm has base 10. So our whiplash would be 10 to the power of 1 would equal our arguments, or I guess our one argument, 8x plus 4 over the x plus 1. In order to get rid of a division, we'd have to multiply both sides by an x plus 1. So we multiply both sides by an x plus 1. On the left-hand side, we'd have a 10x plus 10. Our x plus 1 and x plus 1 cancel off, and we'd be left with an 8x plus 4 on the right-hand side. Our next steps would be to move our x's to one side and our numbers that don't have x's to the other side. So I can subtract my 8x, and I can subtract my 10, so that I would have a 2x equals negative 6. And last but not least, to get the x by itself, I would divide both sides by 2. So our answer here is that x equals -3. So I'm not going to work. We're going to do our check in a second. We're going to do our last example on this page first. So if we go back to our logarithmic laws, there's technically two ways of doing this. There's one way that sometimes doesn't give us both answers, but I'll show both of those methods. The first thing is you want to try and get rid of that squared. Really having that squared isn't always the nicest. And using our log laws, that exponent would just go out in front. So it would be the same as 2 log base 2 of an x plus 3. And that would equal 4. Now we don't even have our log by itself. So in order to get that logarithm by itself, we would have to first divide both sides by 2. So we'd have the log base 2 of an x plus 3 equals 2. Now we can apply our whiplash. 2 to the power of 2 would equal an x plus 3. Now we know that 2 squared is 4. And we would subtract 3 from both sides. And therefore, that doesn't look very nice. Therefore, x would equal 1. So what we're going to do is we're going to check this, and then I'll show you another possible solution, and then we're going to go back to that B example. So for our check, what we want to do is we plug our 1 back into our equation. So if we have our log base 2 of 1 plus 3, make that actually look like a plus 3 squared, would equal 4. So we'd have log base 2 of 1 plus 3 is 4 squared equals 4. 4 squared. So we have 2 to the power of 4. Using our whiplash would equal a 4 squared. Well, 4 squared is 16, and 2 to the power of 4 is 16. So our answer of x equals 1 is all good. But here's where another possible answer comes in. Sometimes people don't bring that 2 out. So we'd have a log base 2 of that x plus 3 squared. And they want to fully distribute this out. So an x plus 3 squared would be an x squared plus 6x plus 9 would equal 4. Now we can still do our whiplash, 2 to the power of 4. Now, I'm just going to evaluate it right away. 16 would equal x squared plus 6x plus 9. And then we want to get one side equal 0. So we subtract our 16. The writing utensil's not working the superest. We'd have 0 equal to x squared plus 6x minus 7. So then we find out our product sum. Product of -7, sum of positive 6, will be an x plus 7 and x subtract 1, giving us two answers of x equals -7 and x equals 1. Well, we already know that our answer is 1. So the 1 is good. But why don't we have -7 as another answer? And where that comes down to, it doesn't say in the question, but I do need to put it in there. It talks about what our restrictions are. Now, I have that in writing above here. The logarithm of so When solving a logarithmic equation, identify whether any roots are extraneous by substituting to the original equation and determining whether all the logarithms are defined. Basically, the logarithm of 0 or a negative number is undefined. Meaning our argument, that x plus 3 has to be greater than 0. So by solving for our x would have to be greater than negative 3. Negative 7 is not greater than negative 3, which means that that is not one of our answers. That's one of our extraneous roots. Abbreviation, x root, meaning that our only answer is 1. Now we're going to come back up here. We're going to come back into our check here. So by plugging negative 3 in, log of 8 multiplied by negative 3 plus 4 would equal 1 plus the, well, I'm plugging into the absolute original equation, log of a negative 3 plus 1. So in here we'd have the log of, we're going to evaluate all as 1, negative 24 plus 4 would be a negative 20, would equal 1 plus the log of negative 2. Now these ones aren't really the superest to evaluate, but we could quickly do a little check here. We do that change of base property because our log is a base 10. So if we type into our calculator the log of negative 20 and divide it by the log of 10, what does that equal? Well, if you plug that into your calculator, you don't get an answer, you get an error. Because we can't find the log of a negative number, just the same as we would not be able to find out the log of negative 2. If we were to type that into our calculator, the log of negative 2 divided by the log of 10, it would also give us a non-answer, an error. And that's because when we talk about our restrictions, I'm kind of bleeding into the next equation a little bit, but our 8x plus 4 has to be greater than 0. So by manipulating this, we'd say that our x is greater than a negative 1/2. And our other one, our x plus 1, also has to be greater than 0. So plus 1 has to be greater than 0, which means our x has to be greater than negative 1. But there's one of these two restrictions that's more dominant than the other. And I like talking about this using a number line, because negative 1 is there, and negative 1/2 is bigger than negative 1. So if we talk about values that are greater than negative 1, whenever circle, we're going that way, and are greater than negative 1/2 would be those ones. The one that would be more dominant than the other would be this x is greater than negative 1/2, because not all of our answers that are greater than negative 1 are also greater than negative 1/2. And if we go back to our question, x equaling negative 3, well, our answer is not greater than negative 1/2. Negative 3 is not bigger than a negative 1/2. So it means that x can't equal negative 3. In this question, we have a null set or a no solution. And this is a question that just doesn't work. Now we go into some of our real nitty-gritty of our solving the logarithms. On the front side, and this is what I have to move to this side, it's basically if we have the same logarithm of an argument equal to another logarithm with the same base equal argument, it means that our arguments are equal. So that's where we have that 2 to the power of x equals 2 to the power of 5. Well, we have the same base. That just means that our exponents are equal. If our exponents are equal, then we could technically just make them to have the same base. So we can change our base to 3. 3 to the power of x equals 3 to the power of 5. Well, it's going to still work. And that's what we're going to do here. And the idea behind it is when we have an exponential, if we take the logarithm of both sides, the logarithm of 4x, it would still equal the logarithm of 605. Because all we're doing is we're taking the log of both sides. So what's the benefit to this? Well, it's using our exponent law, or sorry, not exponent, our logarithmic laws to get rid of that exponent. Because exponentials and logarithms are inverses of each other, they help to essentially cancel each other out. So instead of having this exponential and having to go through a whole bunch of trial and error to find out 4 to the power of whatever it is equals 605, we can apply our logarithmic laws to bring that x out in front and get rid of that exponential. Now, as soon as we get our logarithm by itself, we're trying to isolate our x. Well, in order to get rid of this is x multiplied by the log of 4. So the only way to get rid of a multiplication is to divide. And what are we dividing by? We're going to divide by the log of 4. So the log of 4 is going to cancel off with the log of 4, and x would equal the log of 605 divided by the log of 4. Now we have to be careful when we plug this into our calculator, because some calculators, what they will do is they will open up this bracket. So please make sure you close that bracket. Yes, I know that they're called parentheses, it's just easier to call it bracket. At the same time, the more complicated that we get, and we'll see that in our some of our next examples, basically open bracket, close the bracket, and when we type that into our calculator, the value of x will be 4.62. So if you did do 4 to the power of 4.62, you get pretty dang close to 605. Now, if you want to be more accurate, if you want to go to, what is this called? 9 decimal places, 4.620395666. And you're going to be pretty much as close to that 605 as possible. The only other way to do it is actually using 4 to the power of log 605 divided by log 4, all in brackets, all that kind of jazz, and you get exactly 605. But this question, I'm only expecting you to have 2 decimal places. In this next example, we have 8 multiplied by 3 to the power of 2x equals 568. Now, just like our last equation, we can take the logarithm of both sides. But what we need to see is that the logarithm only gets rid, or helps us to get rid of those exponentials. It doesn't help us to get rid of a multiplication. The only way we can get rid of a multiplication is through a division. So that would be our first step in this type of question. 3 to the power of 2x would equal 568 divided by 8, 71. Now, just like we've done before, we could use a whole bunch of trial and error, find out 3 to the power of what gives us 71, and go through there. But this allows us to, yes, technically, in a question, as we get through to other questions, the trial and error will actually be a little bit shorter than this, but we will get more exact answers by using our methods here. So what we need to do is we're going to take the logarithm of both sides. The logarithm of a 3 to the power of 2x equaling the logarithm of 71. I'm going to try and stay nice and color-coded here just to help illustrate some of the operations and all that. Now when we have that logarithm, it allows us to evaluate these exponents. So we can bring that 2x in front. 2x log of 3 would equal the log of 71. So we have 2 times x times the log of 3 equaling the log of 71. Well, the only way that we can get our x by itself is by dividing both by a 2 and by the log 3. Because what we need to realize is that this log 3 is just a number. We can type log 3 into our calculator. Log 3 is 0.477121255. So we're just dividing by 2 times that. Meaning that our x would be by itself. I'm just going to use my blues, 2 log 3. So what we're going to do is we're going to type into our calculator the log of 71 divided by 2 log 3. Now in order to be extra careful, the more complicated that our numerator and denominator are going to get, put it in parentheses. And keep in mind, once again, that some calculators open that parenthesis, make sure you close it. It's going to make sure that your answers stay accurate, and it's a good habit to have as we go into even more complex equations the further that we go. And when we do type that into our calculator, log of 70 divided by parenthesis 2 log of 3. Our x value would equal 1.94. Now, that equal sign I really do not like. (1.940029.217). 2 decimal places. So if we were to plug that in and take 8 multiplied by 3 to the power of 2 times 1.94, we're going to get pretty dang close to 568. Next one's going to get a little bit more complicated. So we just have to take it nice and slow. We're going to take the log of both sides. Now, so the log of 2 to the power of x plus 1 would equal the log of 3 to the power of x. Logarithms and exponentials help us to bring that exponential in front. But this is a binomial. So what we're going to do with this binomial is we're going to put it into some parentheses. Because technically, we could put parentheses around there. It's not going to change our work. Now, I'm just going to write my numbers. And we bring that x out in front. So we have x plus 1 multiplied by the log of 2 equal an x multiplied by the log of 3. Now what you're going to see is a lot of our work here, we have this x on the left side, x on the right side. What we're going to eventually do is we're going to get our x terms to one side. But before we do that, we're going to want to distribute our x plus 1 onto our log of 2. We're going to multiply x by log 2 to give us an x log 2. We distribute a 1 onto a log 2. I can write the 1, doesn't really matter. But 1 multiplied by log 2 would be a 1 log 2. Equal x log 3. Now that we have everything in one aspect, or in one line, we want to get our x's to one side and our non-x's to the other side. both ways will still work. What I'm going to do here is I'm actually going to subtract my x log 2 from the left side and subtract an x log 2 from the right side. Now a log 3 and a log 2 are not the same. So we'd have a log 2 on the left side, and it would equal an x log 3 subtract an x log 2. Just keeping some colors the same on the right side. And this isn't the only way. We could actually we could subtract this log 2 and we could subtract the x log 3 over, and we'd have it look a little bit different. It's going to give us the same answer. But the tricky part here is we need to get our x's, we need to get rid of our x here. Or in other words, we need to combine our x's into one aspect. In order to do that, this is x multiplied by log 3 and this is x multiplied by log 2. They have a greatest common factor of x. So we can factor an x from our right side. We factor an x from a log 3, we'd have an x log 3. We factor an x from an x log 2, and we'd have a subtract log 2. So I'm just going to put my logs down. So log 3 subtract log 2. On the left-hand side, I just have 2. Sorry, more specifically, the log of 2. Now, just like we have in all of our other questions, this x, we just have to divide by that log 4. This x, we divide by the 2 in the log 3. And here, to get our x by itself, we divide the entire side by a log 3 subtract log 2. So the value of x, I'm just going to put a whole bunch of logs in here. Would be the log of 2 divided by a log 3 subtract log 2. Now, just like in B, the more complicated that our question gets, the more you're going to have to make sure you put your parentheses. And once again, your calculator may or may not add those parentheses in there. So just be careful. If you're doing these questions along, make sure you're typing them in. Just know whether your calculator needs those parentheses or not, so you can accurately get an answer of 2 divided by, in parentheses, log 3 subtracting a log 2. One point seven. Oh, come on. 1.71. So just as a quick check, if I did go to the power of 1.7, I don't know, it's not like my sevens. So that would be a to the power of 2.71. Does that equal 3 to the power of 1.71? I type those into my calculator. 2 to the power of 2.71 is 6.5432. And if I go 3 to the power of 1.71, 6.5445, you know what? That's pretty dang close. So yeah, we're good. Now the most complex one, we just have to be really careful when we're plugging into our calculator. So there's nothing to get rid of, but we can take the logarithm of both sides. My writing utensil doesn't like my G's, it doesn't like my sevens. Again, it likes my 2. I don't know why. Anyways, 2x minus 1, not 2. And 3 power of x plus 2. Our logarithm just helps us to evaluate these exponentials, so we bring them out in front. We have a 2x minus 1 equal to x minus 1 log of 4. That 2x minus 1, I like putting in parentheses. Same thing with this x plus 2 log of 3. Now our work here is because of that binomial. We have to distribute that onto our log 4. And this one, this x plus 2, also has to get distributed onto our log 3. So I'm just going to write a whole bunch of my blues. 2x log 4 subtract a log 4 would equal an x log 3. I'm just leaving the space for my logs. Add a 2 log 3. Alright. So in our ideal situation, we want to get our x's to one side and our non-x's to the other side. Let's see. Multiple ways. This one is going to make more sense to move our x's to the left side just so we have a lot more positives. We can move our x's to the right side. It's not going to change our answer. But I definitely want to make sure I do my operations correctly. So I'd have to subtract my x log 3. We do that on the right side. That's gone. So we'd have on the left side a 2x log 4, subtract an x log 3. And it would equal, now we have this 2 log 3, but we're going to have to make sure we subtract. I have to check my sensitivity on this writing utensil. Subtract that log 4 from both sides. Come on. There we go. So on the right side, we have a 2 log 3, subtract a log 4. And then we want to factor that x out of that left side. So we factor that x out. We'd have to be left with a 2 log 4, subtract a log 3. Apparently I have to take my writing a little bit slower. So actually the register is nice. Subtract 4. Okay. Now that our x is isolated, we can divide that 2 log 4. Come on. Write the G. Good G. Come on. And do that on both sides. Oh. Come on. Maybe my connection's not the best right now. Alright. So make sure you type into your calculator nice. I'm just going to leave everything black here. Yeah. 2 log 3, subtract. Looks like I might have to do some calibration with my writing utensil. 2 log 4, subtract log. Oh, that's not even supposed to be a 3. Sorry, that's supposed to be a 3. Subtract. Alright. Now, be careful when you're plugging it in. Again, parentheses. That's not, still not a 4. Now there's that one. That's a 3. That's a 3. Put in brackets. Alright. Nice and carefully. 2 log of 3. Putting my parentheses. Subtracting a log of 4. Divided by, again in parentheses, 2 log of 4. Subtracting a log of 3. Zero point 4.8. Alright, we're only going to do the one example on the back because it talks about dinosaurs. So paleontologists can estimate the size of a dinosaur from incomplete skeletal remains. For a carnivorous dinosaur, the relationship between the length s in meters of a skull and the body mass m in kilograms can be expressed using the logarithmic equation 3.6022 log s equals log m, subtracting 3.4444. Determine the body mass to the nearest kilogram of an Albertosaurus with a skull length of 0.78 meters. So, S stands for skull length, M stands for its body mass in kilograms. If it has a skull length of 0.78, 3.6022, it means that 0.78 goes in for the S. Log of M, subtract 3.4444. So right now, our only variable is this m. So we need to get our m term by itself. When we do that, we just have to add our 3.4444. (6022) log of 0.78 add 3.4444, which is equal to log m. This entire left side is just a number. At the same time, our logarithm m is log base 10. So our m value is by taking our 10 and raising it to the power of a 3.6022 log of 0.78, add 3.4444. We can type all of that into our calculator, put into parentheses, and just be careful. So when I plug that into my calculator, my 10 to the power of, and I'm just going to use my parentheses, 0.6022 log of, my calculator opens up that parentheses, so I make sure I close that. And I add my 3.4444. The mass of this Albertosaurus would be 1,136.85 kilograms. Now at the same time, I have to make sure I read the question. Determine the body mass to the nearest kilogram, 1137. So the mass of this Albertosaurus would be about, well, let's see, if we convert that into pounds, 2.2462, be about 2,500 pounds. Not going to worry about this example. That allows you to rock and roll. That's fun.